welcome to GOTO Unscripted episode with Oscar Beijbom. Today we have something really, really awesome to cook, and who else to have than Oscar himself. So, Oscar, let's just begin by you introducing yourself. Like, who are you? What are you up to? And let's just keep this up and going.
Cool. Yeah, thanks for having me, Prayson. I'm excited to be here. So my name is Oscar Beijbom. I'm currently co-founder of Nyckel. I'm even wearing the t-shirt for those that are watching this on video. I've done applied machine learning for the last 20 years. My previous job was in the self-driving car industry, where I ran a pretty large team, I'd say about 100 engineers, doing basically the full stack experience of like delivering an AI that can drive a car, right? So the infrastructure, all the data mining, all the data selection, the actual modeling teams that try and figure out which networks to use, and a team devoted actually to metrics, performance analytics. So those are my last two jobs. I can go further back if you want, but I don't want to bore your audience.
No, definitely. So I think if this was also one of the subjects I'm really excited to hear about, is this autonomous car, like self-driving cars. So it has been, just thinking about it, it's a bit crazy, right? We started with a horse pulling a carriage, then we remove the horse and have a horseless carriage, and now it seems we're going back to the horse again, but now the horse is somehow a robot, Oscar. So if we start actually toying this idea, like how do we even begin? Where do we even start talking about self-driving cars?
Yeah, I mean, I think, do you mean the origin of the technology, or
the whole, if we even start from scratch, how do we even start coming with an idea of collecting data, or thinking of how should everything be from so all the components that take us to the first step of building a self-driving vehicle.
I see.
Yeah.
Got it. Yeah, I mean, it's one of those things that, so the most recent sort of boom or push to build a self-driving car started with the DARPA Grand Challenge about 10 years ago. So there was a US government competition. The city, a bunch of top universities basically competed in putting a car together that was supposed to drive on basically in an unknown area. So that showed a lot of promise, and people started feeling that, okay, the technology might be actually ready for this. So the big teams were like CMU, Stanford, MIT, basically. And they all were what I would say, quote unquote, classic roboticists. Or, of course, they don't think of themselves as classic. They think of themselves as cutting edge, latest advances in probabilistic robotics, right? But it's still a worldview where it's more or less of a programmed, hand engineered robotic system that perceives the world, reasons about it in a probabilistic way, right, and then make the right moves. So that's, most of the company, including the one I joined out of when I finished my research, it's called Autonomy. It was an MIT-based company. So it was a robotics-based company, and there was no machine learning at all in the pipeline, right? And what typically happens is that in the perception system, that's typically where machine learning gets its foothold, right? And what happens is that the main sensor during the DARPA competition was a LiDAR, right? So you just get this point cloud back, and it's an amazing sensor, right? So you get a 3D representation of the world around the vehicle. And you can, by doing stuff like background or background subtraction, you can actually sort of figure out which points are, quote unquote, foreground and are moving around in the world. You can start clustering them. You can write sort of step by step, pretty reasonable perception system based on that. But there are obviously edge cases where this won't work, like a pedestrian that stands next to a pole on a LiDAR, for example. They look very similar, but obviously a pedestrian you need to treat very differently than a pole, because even if they're standing still, they may start walking any time. So basically, once companies started doing this seriously, they realized they need also cameras and computer vision. And once you have cameras, you sort of you have no choice but to use machine learning, right? So that's where it started. So I was hired to do originally just as a machine learning research engineer to help bring that up. Now, finally, to your question, you're saying, in this world now that we are doing machine learning, what are the pieces? I think that's what you were getting to.
Yes.
Yeah.
Because it's one thing collecting data. It's one thing telling the machine this is a pedestrian or this is the road, follow these kind of things, right? But we know we have all these things we have all these things in play: incoming data, analyzing of the data, and then making that decision, right? So all these components needs to work together, and not just they need to work together in a very rapidly way. So you have computation and speed that one has to take into consideration. No.
Yeah. I mean, machine learning is this it's almost this like false promise of a wonderful world where you quote unquote just annotate data and then it just works. You don't have to program anything and it improves itself and so on. But what ends up happening is that the amount of effort you need to put into what I call the data engine is immense. Because you're basically just compiling data onto code, right? And if your data has issues, your code will have issues. So you end up this basically endless cycle of trying your model on new data, seeing where the issues are. And that's not easy, right? It's not easy. I mean, obviously, if you're doing it manually with the human in the loop, it's easy because you can just see what mistakes are being made. But if you're doing it on automated, on aggregate, it's actually not that easy to even write down specifically what you should be looking for. So errors, but especially if you're thinking about a self-driving car, certain errors are much worse than other errors, right? If I see a bird in the sky and I say that's like, I don't detect a bird in the sky, that doesn't matter. But if I don't detect like a dog in front of me on the road, that's actually really bad, right? So you need to basically develop this data engine or this cycle of identifying issues and retraining. And that's just one of the cycles you need. The other cycle is, as you mentioned, you want to iterate quickly. So what does it mean to iterate quickly? Well, you typically need to train models very quickly. Because if you're not careful, retraining could take a couple of days. So now you're like in a cycle where you're only improving your system like once or twice a week, and that's obviously not where you want to be. So now you're suddenly in the business of building up a highly scalable like GPU cluster and training using, like scaling up. Like most of the toolboxes have very good support for like multi GPU on a single node, but now you go beyond that. So now you have multiple nodes. Now you have to like figure out how to accumulate the gradients and set tuning and learning rate and all those other parameters for that all to make sense. So yeah, it's a lot.
So now I'm gonna rewind back when it comes to machine learning and data collection. So when we usually build machine learning, classically we usually just collect some examples to which the algorithm has to learn. So when it comes to self-driving, how do you go about that? Do you just put drivers into a car and they just have to go through the streets? And then that's how we gather their data and their decision to stop and look around. So how does this play in?
Yes, that's a good question. Yeah, so typically it's a bit of a bootstrapping thing where you start with just fully manual drives to get like maybe just nominal data, like normal data. And then you train the first model and you sort of bring up the self-driving capacity in that area. And then, you begin a long cycle. It could be several years where you have a safety driver that is in the car ready to take over, but the car is actually driving autonomously, right? And a lot of times you could have errors. Depends on how, like I said, it depends on how severe the error is. So you can miss it. You cannot detect the pedestrian, but the pedestrian maybe never interferes with the trajectory of the vehicle, so it doesn't, quote unquote, matter, or it doesn't result in a takeover, right? Basically, if the AV, autonomous vehicle, makes a bad enough mistake, the human will take over, and that's a very good signal for like something is wrong here, right? So you can collect data around that timestamp. But there are other issues that you want to capture because just to be more efficient, where the AV didn't actually stop. There was something else in a subcomponent that didn't work.
So we know that in machine learning, when we get the data and everything, there is like this boundaries of which we can collect our data from. But then here we are dealing with the real world, to which one does not know that the next day is something like a marathon where there will be a lot of people running. And during our training, we never consider, there will be this event in town with so many people around, etc., etc. So what do we do about all these things? Do you usually go into simulations of different scenarios to make sure that you capture almost as much possible of the real world before putting the car out there?
Yeah, so that's a great question. I mean, I want to say that the company I work for, Motional, Autonomy, and then Motional, there's this very gradual roll-up that I thought was compelling. So it's not like you build the system and then you just release it. What's going to happen, and what Cruise is doing now, I'm sure, even though I don't work at Cruise. So Cruise, for the listeners, is another AV company that recently, actually just a few days ago, got approval to run fully autonomous robotaxis in San Francisco. So they will be the first company with paying customers, I should clarify. So as far as I know, that's the first. So what happens is that it's not like you go from 0 to fully autonomous. You go from 0 to having basically one remote operator per vehicle. Okay. So of course that remote is not going to be real time because it's because of the delays in telecommunication. But you have a very close loop with a human that observes everything that's going. So getting back to your point, and then, sorry, let me just finish that train of thought. Basically what you can do is then smoothly go and say, okay, one person is now remotely operating 2 and 3. So you can roll back the number of people you need. Now to your point, with if there are like these events that happen, I think initially they will just not drive that day. They will literally be talking to the city and like finding out when these big events are happening and just not drive. Or if they didn't hear about it from the city and they start seeing it in their sensor data, right, because they have cameras, they will just, okay, we're just closing down. So from a safety perspective, from a deployment perspective, that's what you do to like not get into trouble when that happens. Does that make sense?
Mm-hmm.
But then I think what you were really asking was like, how do we learn from that? How do we actually, in the end, solve that problem? And yeah, I mean, I think you're right. I personally don't like using simulated data to test on. Like I always want my test set to be real data. So what I would do if I was, in Cruise and there was this demonstration is that I would go next to it with a fully manual and I would just collect the data, right? I would just collect the data and I would add it to my test or validation set. And then, of course, to train, then when you train, as you know, as your listeners know, I'm sure you need like a diverse set of data, you need a lot of data. So then you might need to go to simulation to get what you need. But you're still evaluating on real data.
Okay. It's because in my chain of thought, I was thinking of when it comes to self or autonomous car, I want to be at the airport and just call my car to come pick me up. Right? So in this case, there is no human in the car in the first place. I am calling my car, hey, I'm landing at this time. Can you come in the basement at this airport at this time? And I'm like,
right.
But, at this time, we're not even in that level. At this time, we're just thinking of autonomous car, but not being left for it to drive by itself.
Yeah, I mean, that's a big controversy, right? So Tesla is basically trying to build what you're saying, which is a car that, and they take on a very, very difficult problem, right? Because they are basically doing what you're saying. They're like building a car and then just giving it out to the public, and they can't really control. I mean, they have ways to say, okay, we disengage, like the autopilot is only available in certain areas and under certain circumstances of the data. But still, like, it's just this open world problem where they just release these vehicles. And I think that's the controversy around Tesla. Now, I think the jury is still out on whether or not they are saving lives. I suspect they still are saving lives because they avoid a lot of issues with fatigue and so on. But there are, there's been real accidents, right, with Tesla, and people have died because of their deployments. So that's the business case of Tesla, which is different from Motional, Autonomy, Cruise, Waymo, where there's a robotaxi service where you don't call your car, quote unquote, you call a robotaxi.
Okay, yeah.
And that fleet is monitored very closely.
Okay. So I know I am bombarding you with so many questions, but I think that's my role here. to fry you a bit. Okay, so
no, it's good.
I
like talking about this.
So now comes another heavy question. So when we talk about autonomous car, here comes a question. Do you think we are ready for such kind of technology? Do you think our cities and the people in general are ready to allow autonomous car to start roaming our streets?
I don't know. There's so many ways it can play out. So the utopia that part of the reason I signed on to this is there is this utopic vision where essentially people will not own cars anymore. Like, the taxes will become so cheap that car ownership goes down, and essentially this is this shared fleet of transportation, right? And if you go to that, I call it the utopia because what happens then in that world is that I don't know how much time you spent in the United States or in California, but the cities are very dominated by cars, and not just by cars, by the roads, but by the parking lots. So like when they build, there's building codes to say like X square foot per indoor should have X square foot of parking spots. So the cities become very sparse and uninteresting. So there's a world where if you can reclaim all those parking spots, you can have denser, more interesting, more walkable spaces in cities, right? And in addition, people don't need to own cars, right? So it'll be cheaper for people to get around, and it'll be less carbon emissions in general, right? Because you just need to produce much fewer vehicles. So that's the utopian vision that I think is very interesting. But there's a dystopian vision as well that sort of goes like this, where if the cars drive themselves and you can sleep in the car, everyone still buys a car. Everyone still buys as many cars because they like having their own cars. But now you can sleep in the car, and that changes your math on how far you're willing to commute. So you can be commuting for 2 hours, even 3 hours. Say you get up at 4 a.m. and or you even go to sleep in your car, right? And then at 3 a.m., the car will just start driving you to work, and you wake up at 8 a.m. in front of your office. And of course, that's like, it allows people to live in the countryside and outside of urban areas, but it's an immense waste of energy, right? Obviously, that energy could come from green sources, but it's still like kind of a crazy thought. And I don't think the cities are ready for that at all, right? Because you have so much more traffic, and the congestion would be just immense.
Mm-hmm. What do you think the adoption of autonomous car will depend on a massive, like every one of us joining this kind of journey? Then we only have robots against robots driving cars.
No, I mean, certainly the way the technology is being developed is assuming human drivers.
Okay.
With all that complexity. So I think you can, it's just, the question is like, is it going to lead to less car ownership and more sharing or not? And I think it's very hard to know which way it's going to go.
Yeah.
And
Nice.
the cities, I mean, I don't know, I can't speak for the cities in Europe, but the cities in the US, I mean, US government is very reactionary. They don't really plan. They don't really think ahead or have big visions, at least not at the city and state level, right? It's just kind of letting private enterprise run free, and then they react to whatever happens, right? With the scooters, right? That was suddenly there are scooters everywhere. And I think that happens in Sweden as well when I go to visit, and the cities just have to react to it as best they can.
Okay. Well, Oscar, let's go back to the basics. So back to what we do most. So can you, what's your role as a developer when it comes to all this? So what does your day-to-day look like when it comes to building autonomous cars?
Yeah, I mean, that's a good question. And I mean, so obviously I joined as a individual contributor, and then I ran a small team of, 5 to 10. And then suddenly I ran 3 of those teams. And then suddenly I ran like teams, like I ended up with 100 people or so. And obviously my day-to-day changed a lot during that time. But I think if we focus on, maybe most of your listeners are, engineers or aspiring engineers, right? I think one myth, if you apply for a machine learning engineering job, and at least in the US, it's extremely popular, like at universities, a lot of people focusing on machine learning because it's seen as sort of, the next hot thing. The expectation is that you spend a lot of time, like if you look at Kaggle or like any of these data sets or ImageNet, the data is given to you and the metric is given to you. So for ImageNet, it's like the top 1 accuracy or the top 5 accuracy. And the data is fixed, and now you're just working on the algorithm, right? So you have this sort of nice playground where all you're doing is tweaking hyperparameters of your neural network, trying new learning strategies, whatever, right? The sort of quote-unquote core machine learning. But I think what happens in practice is that first of all, the data is not fixed, right? So it's up to you to find your own data and find good data. And then the objective function is also not fixed. And that's something it's very, very difficult for AV to figure out what the objective function is. Obviously, at the system level, it's pretty straightforward in the sense that you want as few accidents as possible. You want to go from point A to point B as fast as possible. And there's probably like something around comfort as well, so you don't get seasick. So it's like those 3 components of the system level metric. But imagine now you're a computer vision engineer working on pedestrian detection. If you go to the textbook computer vision texts, it would say, okay, well, if you're doing detection, you should use mean average precision, right? And that's the metric that you should be optimizing for. But in any given application, it's not clear. In fact, I would argue it's never the best objective function, right? Your objective function should somehow be tied to the next subsystem downstream. So if I make a certain type of error in this example, how does that affect the planner, right? That sits in the AV and tries to plan the route. And how does that then affect the controller? And then how does that then affect the ride and the final quality for the consumer or for the customer? So that's something we actually thought. We actually wrote a few papers on that as well. Like, how do you think about? I call it metrics back propagation, or like variational analysis on if my subsystem performs like this, how does that affect the final system performance? So yeah, I guess getting back to your question, sorry I keep going on tangents, but the day to day, what does that mean for the day to day? Well, I think it just means, it depends on the size of the team, right? So typically you would have a team, at least we had a team for every one of these components. But if assuming it's a smaller team and you're kind of in touching everything, you're probably going to be working a lot on just like speed of iteration cycles. So you're going to be like making sure you can run experiments and like quickly and see the results quickly and compare to other results. Like, I ran these 20 things. How do I visualize for myself which of these things work better? And how do I define better, right? And then once you have that figured out, you're going to go to, well, okay, how do I figure out which data to train on, and how do I? And also that is a lot of infrastructure, right?
Yeah. But I usually say that 90% or even more than 90% of machine learning is surrounding around data and how you handle data. And then the last small percent is the algorithms. So let's say, okay, we have our data streaming and we have everything flowing well. We are in this cargo utopia, but at least we are fighting with the objectives yet. So when we dive deep, when you guys begin building your models, is there like preferable languages that you probably use, Julia, Python, or whatever, and how does it affect your daily flow?
Got it. Yeah, so we were a Python shop exclusively, and we were actually a very early adapter of PyTorch when it came out. Because I had used Caffe previously, the Berkeley deep learning framework, that was falling out of fashion, and TensorFlow was sort of the predominant one. I didn't particularly like TensorFlow at the time. So when PyTorch came out, we jumped on that, and I think that was the right decision. I think PyTorch is a wonderful piece of software. So that's, if you want to get into the space, becoming fluent in PyTorch, I think is a good idea.
But then, because I've heard a lot of complaint when it comes to Python, and of course I know PyTorch and TensorFlow and NumPy are written in a deep language such as C, but how does this affect the speed? Because I hear some say, well, maybe you should use something like Julia, or maybe you should go to C++. How does Python affect? Because we know we're dealing with very, what you call like, the system's response needs to be almost like live, from the sensor capturing something for the car to brake. It like,
I see.
Yeah.
Oh, okay. Yeah. So my team and my org was a Python shop, but in a way, what we did was basically compile data into networks, right? Weights. And then, but the code that operated the vehicle was C++.
Okay. Yeah.
Yes. Yeah. And as you point out, of course, the real time, like the latency of the system is extremely important. So what we spend a lot of time on is optimizing the inference speed of the network by the architecture of the backbone itself, right? But also using stuff like TensorRT, which I think is a really powerful runtime optimizer for NVIDIA GPUs. And there's also things like pruning and quantization. So you go to 8-bit precision, or you remove the connections in the network that you don't need. So we spent a lot of time on that to give a very, very light, fast kernel. And we were running object detection and segmentation and classification at 200 hertz in the end on a single GPU.
Okay, yeah.
In fact, we were running like 8 cameras on one GPU at 200 hertz.
Okay, nice. Okay, super. So now we are going to the next part. So we have our data, we have our models. When is the model good enough to go into production. Like, how much error can you tolerate? So how do you even start answering this part of the metrics? That what percentage of issues we can allow to deploy this model?
I mean, so if I had a quarter or a dime for every time I was fighting with our safety team, basically. So again, there's these two cultures that were clashing. There was the automotive industry, traditionals, where you would design a system and the specifications of that system, right, ahead of time, and then you would sort of code to spec, and then you would check if it works, right? So that's how most vehicles are built, like the auto industry and most industrial systems. And the reality is that, but that's not how software is built, right? Software is more like you put something together, you ship it, and then you find issues and you iterate, right? So you have the software world where like deep learning belongs, right? And then you have these robotics or like industrial verification processes on one side. And we didn't actually make much progress until we essentially fired all the quote unquote safety people. Because it's impossible. Like you can't put up these hard barriers for yourself and say, okay, until it's 90% accurate, I'm going to ship. Because, and the thing is that it's not like I'm against having these goals, right? It's more like 90% on what, right? It's 90% on some data set, right? And of course, and the point is that I can give you 100% on a data set, but it's not going to be like the hard data. And you can only find the hard data by deploying an intermediate product, like we talked about it earlier in this conversation, like deploying some earlier version of your system in production and then finding issues and learning from them. So you like the process of like finding out the issues, you can only do that when you're like deploying on scale, right? Because the more rare the issues are, you mentioned this marching band, right? They don't happen that often. So you need to just be out there and find them.
Yeah, but when we talk about what is at stake here, like there are some errors which are more tolerable than the other.
Yeah.
So if I crash a company's business because my model predicted a return of investment that did not pin up, so probably some people will lose their job, or probably they will fire the data science team. but no one know what we call this risk kind of issue. Like when we talk about the car, we can talk about it killing someone, which would be there. So here the weight becomes really heavy compared to the other one. Right? So in this case as well, like, okay, when do we say we are okay enough? But you answer this by saying, okay, so in your scenario, you will always have someone in the car to make sure that such an event does not happen.
Yeah, I mean, you have someone in the car initially, and then you would have someone outside the car, remotely ready. But yeah, so I mean, I totally agree with you. Like, I feel like I don't have a fully satisfactory answer.
No.
All I can say is, even if you like this sort of concept of, as soon as you have machine learning involved in a system, like trying to define beforehand goals or like performance level metrics is a little bit of a false errand, because it's really conditioned on the type of data that you're measuring on. And it's hard to know. Like, it's not like, oh, if you talk about pedestrian detection, you need pedestrians at certain distances. You probably also need them at certain weather conditions, right? And then you need them at certain like color clothes, right? Because it's just going to look different. And the list goes on and on. So you end up with these strata of your data that are like combinatorial. So it's very hard to exhaustively test all the different strata.
Okay, let's bench that one under the bridge for now and actually go to the progressively climbing to all the issues that I think you encounter in any machine learning problem. So let's move on to security. So for once we are having a model, our data, we have the model in place, we have to take things into consideration. But now we have all this connectivity. And with connectivity comes security.
Right.
If someone is outside there and he can control my car, that means a hacker somewhere in, those countries can actually take control of my car. So how does this play in the whole design and the whole autonomous car when it comes to security of someone else taking over control?
Yeah, it's a good question. I must confess, this is something I didn't interact with a lot. I just kind of assumed that it would work. I mean, I know for sure that we decided early to not rely on an internet connection. We don't want any communication between vehicles. Like there's a lot of things you can do potentially where you say, if you have big enough fleet, you can just share information. So you kind of have a shared worldview and you get a better understanding of what's going on. But we decided not to do that because it has too much communication and too much safety risk. Now, but we did decide that we need a remote operator, like I talked about, of the car. So obviously they need to communicate to the car, and so there is an open channel that can be hacked. Yeah, I don't have a good answer for you. I think it's a risk, and I hope they do it right.
It's quite okay. We don't always need to have all the answers now. Okay.
Yeah.
So, well, it seems I have exhausted all my questions. Are there anything you would like to add? Anything that you're burning for that you would like to share with the whole GOTO community?
Yeah, I mean, I guess I'll take just a few seconds to tell you about the company I started with some friend called Nyckel. So we actually did quit my job a couple of months ago and to create a machine learning platform company. And the motivation there was basically I have friends that are software developers that kind of complained about even as much advances that has been in machine learning, it's still like a big lift for someone who doesn't know the technology to bring it into their app or their system. So what we try to do at Nyckel is put a very simple API around the whole machine learning box. So you post your images and your labels to Nyckel, and we will train automatically, basically we do all that stuff that I talked about. Like we just try all the state-of-the-art methods on your data and give you the one that works best. And then you can call that, we deploy it to an endpoint for you immediately. So it's something, frankly, I wish I had at Motional at my previous job, because there's so many situations where even at a big company, even us, we had a big machine learning team. There's so many situations we just need something simple. Like you just like for example, take an image and you just want to know, is my AV in this image? For example, for data mining purposes, right? Well, it's not hard, but it's a lot of work. Like you still have to train something. You have to check that it works. Then you have to deploy that model somewhere so you can call it as part of your data infrastructure or general training infrastructure. So being able to spin up really light, really fast machine learning functions is something I was missing, and something that we are working on.
Okay. Yeah. So here comes a Gartner kind of question. Do you see any autonomous car driving anytime soon within the next 5-10 years?
Yeah, I mean, I am, because in San Francisco, Cruise has been making a lot of progress. So they have an internal autonomous taxi service going. And as far as if I understood the news correctly, they will be opening it up for paying customers soon, or at least they got the permit to do so. I don't know what that means, how soon what that implies about timeline, but yeah, I feel pretty optimistic that they'll do it. And again, it's autonomous in the sense that there's no driver, but I bet you a lot of money there is a remote operator.
Yeah, because here we are talking about the level 5 fully autonomous cars, right?
I see.
Yeah.
So like you mean like the Tesla?
Yes.
The end game for Tesla?
Yeah.
Yeah, I mean, Tesla is, if anyone is going to do it, I have a lot of respect for, Elon Musk, but also Andrej Karpathy, their AI lead there. He's as good as they come as far as like applied machine learning, applied AI. So I think if anyone can pull it off, I think they will. And it's they also take it step by step, right? So they're already doing it on highways, on bigger roads, and then they're parking lots. So they're going to sort of slowly but surely expand the operational domain that they support. So sorry to give you a non-binary answer there, but I think it's happening. It's happening slowly, and I feel pretty optimistic that it will come to fruition.
Yeah, definitely. Well, with that, I will bring this to a conclusion. Thank you so much, Oscar, for your time. And we hope to see you soon again.
Cool. Thanks for having me, Prayson.
Have a good one.
It was great talking to you.